other parts of us, namely me.
Number
not.
34. And again, incline.
Yeah.
Here we go. Number 34. Can you even see this writing on the board from there, Shelby?
Yes.
Not really. Okay, read James number 34, please.
You won't laugh?
Shh.
Ryan and Becca are moving a folding table out of the sunlight. A cup of lemonade with a mass of 0.44 kilograms is on the table. Becca lifts her end of the table before Ryan does, and as a result, the table makes an angle of 15 degrees with the horizontal. Find the components of the cup's weight that are parallel and perpendicular to the plane of the table.
All right. Here we go, Simon Sims. 15 degrees. 15 degrees. Draw your solo cup.
Oh, dang. Oh, I haven't had one of those for
Okay. From the center of the solar cup, which way, Jalen, does gravity point? Yes. Okay. So gravity points down. F of G. F of G is mass times gravity. What's the mass of the cup in the problem? Mass of the cup in the problem is 0.44 kilograms. So we're going to actually calculate these things. Okay? So F of G, in other words, if the cup were sitting on the ground and not on a ramp, it would normally weigh how much? Well, it would normally weigh 0.44 kilograms times 9.8 meters per second squared. How many newtons is that? Help me out, Orlando. How many newtons is that? 0.44 times 9.8.
4.312.
4.3 newtons? All right. So 4.3 newtons is what the cup would weigh if it were sitting on the ground and not on a ramp. However, it is on a ramp, is it not? All right. So, now, we have an apparent weight of the cup. And we have a 15-degree angle. Right here, 15 degrees. 15 degrees. Right? All right, do you see a triangle beginning to take shape right now?
I see
I
three
see.
triangles.
All right, well, let me erase this then. Help you guys out.
I still see 3.
Okay? All right, there we go. I'm going to complete the triangle. I'm going to make your little box here because in geometry class, we all know what that box means. What does that box mean?
90 degrees.
Oh, it means 90 degrees. Very good. So this one at the tip here is 15 degrees. Now, we know that this hypotenuse is 4.3 newtons. Okay? So how are we going to find the apparent weight of the cup, which is equivalent to the normal force? How on earth are we going to find that? Well, this is an adjacent leg to the angle. An adjacent leg to the angle. This is a hypotenuse. That's an angle. That's an adjacent leg. A cosine. So, this means this thing here is the cosine of 15 degrees. Okay? Cosine 15 degrees equals adjacent. Sorry, hold on. Cosine 15 degrees equals our adjacent over our hypotenuse, which is the apparent weight we're trying to find over 4.3. So, Shelby, we multiply cosine of 15 degrees times 4.3 newtons. Will you guys please make sure you're in degrees? Degrees, Orlando. Degrees, not radians. Cosine of 15 degrees times 4.3 newtons. And that will give you the apparent weight of the cup, which is the same thing as the normal force. What do you guys get?
4.1.
Sir, 4.15? Excellent job.
Thanks, man.
Excellent. 4.15 newtons. Shelby, can you see this writing at all? You can't, can you? It's like
Some of them
terrible.
can.
Huh?
Some I can, some I can't.
4.15 newtons. So, Wiggins, what's our normal force? It's 4.15 newtons. But hold on, Rodney. Isn't our normal force supposed to be the same thing as our mass times gravity? Isn't it always the same thing?
No,
No, not this time. Why? Because we put it on a ramp.
Put on a ramp.
You're so cute.
Okay? Alright, now, is the cup sliding down the ramp? Is it moving up the ramp? Is it sliding down the ramp? Is it moving up the ramp?
It's
Sliding down?
It's not moving up.
What does it say in the problem? Does it slide down?
It slides down.
No, where?
It can't slide
It does
up.
not slide down.
It is.
Is it sliding down?
Possible, yeah.
No, it's not sliding down. So this force applied and this force of friction, okay, cancel each other out. They're zero. It's not moving. Not moving. Acceleration equals zero. F net equals zero. It's not moving. No applied force, or rather the applied force is the same thing as the frictional force. They cancel each other out because it's not moving. Okay? So, look at that. Your apparent weight and your normal force cancel each other out. One's negative, one's positive. These two guys cancel each other out. So yes, you tipped the cup on the incline, but it hasn't moved. See that? Okay, do we understand that's cosine of theta? We don't understand that? No?
No.
Yeah.
I'm gonna just go ahead and answer the class and say no.
Jim, we're all not moving.
Okay, in the problem, the whole problem said, Becca lifts her into the table. The table makes an angle. Find the component's weight. Did it say the cup was moving?
No.
No, sir. So if the cup is not moving, that means the friction force and the applied force cancel each other out, or they're not there at all. Okay? So it did not mention these. So cross these out, these are zero. And then negative 4.15 and 4.15 cancel each other out. So those are zero. So you have no acceleration, Brianne, right?
No.
And if you have no acceleration, do you have a net force? No, you do not. Now, on the test, okay, I will give you a pre-drawn out diagram of an angle and a theta with the little triangles in it. Okay? And I will give you numbers to put in there, so you don't have to worry about drawing this diagram. But you do need to do the calculations. Does everybody understand why we used cosine? No, sir. That would be sine. What is cosine? Adjacent over the hypotenuse. The hypotenuse is the weight that is on the ground. The adjacent
Don't
right
drink
here
anything from
is the weight that it feels on the ramp.
So, that straight line.
The straight line pointing to the earth is the hypotenuse. The dotted line is the adjacent.
Alright, so straight line weights and the dotted line weight goes straight.
So, nope, wrong way. Here's the cup. Here's the cup on the earth. Cup on a flat table. Flat table, it has the force of gravity, which is mass times gravity. And it has the normal force. Okay? Do I need to use cosine for that? Do I need to use sine for that? I don't need to use any angles for that, do I?
No.
So now that arrow will always pull down towards the center of the earth. Now we're going to take the cup and we're going to tilt the cup 30 degrees. 30 degrees. Well, guess what? The force of gravity that the earth applies to the cup still pulls to the center of the earth. But the normal force does not go directly up anymore. It goes like this.
Yeah.
Okay? Goes like that. I'm going to draw everything from the center of the cup so we can make our little angles. So now it's 30 degrees, okay? Or 15 degrees, excuse me. So now, Wiggins, the normal force and the gravity force has a difference of 15 degrees. And you see this dotted line, this dotted arrow? Dot, 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 dot. It's a pretend arrow. This arrow goes straight to the earth. This pretend arrow, that's how hard the cup is pushing on the ramp. It can't push on the ramp with its full weight like it would if it was flat. So now it's not pushing as hard on the ramp. It's pushing this hard. cosine of 15 degrees times hypotenuse.
Yeah.
Just like if you stood on a hill on a scale, you would weigh less. Just like if you ran down the hill, okay, you would weigh less.
Well, if you attach it to your feet.
Okay?
No, that's like. Have you ever run with snowshoes? I mean, really good big flash. I've never had it either. Maybe it's shoes, so you don't snow, you don't fall.
And
You put things in the snow, so stitches.